Before viewing this video, please read chapters 9 and 10 sections on the Friedman test and McNemar's test. Friedman test is a non-parametric version of the repeated measures ANOVA. The null hypothesis for the Friedman test is that the average ranks of each intervention are the same. So in our example of the observed forced expiratory volume as baseline following endotoxin administration and endotoxin and salbutamol administration, we would first rank the measurements for each subject independently and compute the rank sum for each intervention. So for each subject, we would rank based on the observation and sum those ranks for each intervention. Under the null hypothesis, the interventions will not affect the rankings. Its expected rank sum is the average rank times the sample size. We can quantify how different the treatment rank sums are compared to the expected rank sum by calculating the sum of squared deviations, where RT now is a rank sum for intervention T, and N times K plus 1 over 2 is the average rank that we would expect for each intervention. Finally, we can compute the Friedman statistic as the sum squared deviation over the number of samples times the number of treatments times the number of treatments plus 1 all over 12. For large enough samples where the number of subjects is greater than 9 for the number of treatments equal to 3, or the number of subjects equal to 4 for the number of treatments over 4, the Friedman statistic distribution can be approximated by a chi-square distribution with the degrees of freedom of nu equal to k minus 1, or the number of treatments minus 1. For small samples, the critical value for the Friedman statistics has been tabulated and can be found on page 224 in the text in table 1014. This is a table for the critical values for the Friedman statistics. So in our example then, we calculated the rank sum for each intervention. And with this, we can calculate the sum of the squared deviations. We also calculated our average rank sum, which we would expect for each intervention, and then calculate then our Friedman chi-square statistic. Assuming the Friedman statistic is high or large enough such that the interventions represent 2 or more populations, we can perform pairwise comparison between the tests or interventions using the Wilcoxon sign rank sum test. For each pairwise comparisons, the observations are ranked separately. The critical p-values then must be adjusted for multiple comparisons, for example using the Holm procedure. Recall that we've already entered the forced expiratory volume data into R, and to recall that data, we had the change in volume organized as an array. We created an array that assigned these numbers to the subjects and also to the treatments. The function we'd like to use is called the Friedman test, or Friedman.test function. There are actually 3 formats that we can use to enter the data into the Friedman.test function. One is by a matrix, which is similar to the chi-square test that we had used before, and that is in the form of a contingency table. And in this case then, we would just need to rearrange our data into a table format. So we're going from this array, and we can change the format of this data using a matrix function. So matrix dv, and then we can just specify the number of rows. However, the issue here is that the matrix takes these numbers and assembles this matrix with 4 rows by columns. And so to change this, you can actually say by row equal true, and it will rearrange this data by row to give us the correct contingency table. And this contingency table then we can enter directly into the Friedman test. And so then we can say Friedman.test. This becomes our matrix. And we have an output where our Friedman chi-square statistic is 8. And this is assuming the chi-square statistics in which we have degrees of freedom of k minus 1 and a p-value of 0.01832. However, the sample size is fairly small, and so for exact p-values, I would refer to the table in the text. Now the question may arise when you should follow the statistics given it in R or when you should go by the table. And I would say that if it's tabulated, go by the table. If not, go by the result that you get from R. And so in this case then, if you look in the table with 2 degrees of freedom or 3 treatments and 4 subjects or n equal to 4, chi-square value of 8, or the Friedman chi-square statistic of 8, gives us a p-value of 0.005. So in this case then, we would reject the null hypothesis and assume then that the treatments represent at least 2 populations. Other formats can also be used in the Friedman test. So one other one is you can specify then the data, which is dv, the groups or the treatments in this case will be the variable ttt, and then the blocks, in our case is the subjects. And so entering here, we also get the same result. Another way or another format which we could use a Friedman.test function is through a formula. And so in this case then, we're interested in how the data as a function of treatment or a function of the groups, in which the groups are arranged in blocks or subjects. So there are 3 different formats then in which we could use or enter data into the Friedman test. Repeated measures of nominal data, McNemar's test. There are times when you may need to determine whether or not the proportion of a specific condition in a population changes with a specific intervention. To quantify this, you need to estimate the proportion of your sample with the condition before the intervention, then check how the proportion changes after the intervention. We can organize the data as follows, where we have a condition or proportion before in which so many subjects have the condition and so many subjects do not have the condition. After the intervention, those that had the condition previously, there will be some remaining that still have the condition and some that no longer have the condition. Conversely, after the intervention, those originally that did not have the condition will also not have the condition, but some may have developed the condition. So some subjects, B, that presented the condition before the intervention did not present it afterwards, and some subjects, D, that did not present the condition before the intervention presented it afterwards. The null hypothesis states that the proportions should be the same before and after the intervention. In other words, the changes that we see in the numbers with condition and without condition should be random, and therefore the changes that we see should not affect the overall proportion. In other words, that B and D should be comparable or equal. McNemar's test is a variation of the contingency table method that focuses only on the number of subjects that change their status upon intervention. We use the chi-square statistics, in which we focus on the observations, in which those with a condition beforehand change to no condition after the intervention, and those that did not have the condition before the intervention change to having the condition afterwards. The expected value is going to be based on the average between these two numbers, or the average between the numbers that changed their condition after the intervention. We calculate the chi-square statistic then as before, and we use the Yates correction. So in our example then, we can look at the presence of P7 antigen in breast cancer tumor cells before and after radiation chemotherapy treatment. And so the numbers that we're interested in is in those that were positive that changed negative, and those that were negative that now changed positive. The expected value then would be the average of the number of changes, and we can calculate then this chi-squared value. You can do this by hand, and the degrees of freedom then in this case will be 1, and you can compare it to the chi-squared statistics. We will also do this in R. The data for example on the presence of P7 antigen in breast cancer tumor cells before and after women are treated with radiation and chemotherapy is in table 9-7 on page 201. So in this case, because it's a 2x2 contingency table, I'm going to use the matrix function to create my contingency table. And in this case, I'm going to remember that the matrix creates the matrix by columns. And so in our case then it will be 4, 12, 0, and 14. The number of rows is going to be equal to 2. And so this table then matches the table in 9-7. This is the matrix then that I will enter into McNemar's test. And so in this case then, it's calculated a chi-square value of 10.083 with a degree of freedom 1. And this chi-square statistic gives us a p-value of 0.15%. We can actually look at this graphically, in which we have 1 degree of freedom, we can see then that 10 is going to be very low, as we would expect from our p-value. And we can calculate this then. So that a value of is going to be very low probability on our chi-square statistic. And our null hypothesis then would be false, in that the changes that we see in the populations of positive and negative are not significant. So the treatment did have an effect on the presence of P7 antigen.